this whole story is obviously about heat transport by the ocean. So Mohaline circulation is a big part of the northward heat transport by the ocean. We worry about ocean circulation, sea surface temperatures, how the atmosphere responds to it, the climate, which we'll look at in the next chapter, uh, rain, droughts, snow, etc. But ultimately, the planet is basically trying to move energy, and it does that by creating weather and climate, right? So the oceanic heat budget and heat transport are very critical. We had inferred the poleward heat transport required for the energy balance based on the excess energy in the low latitudes and the deficit energy in the high latitudes. So the dark solid black line here shows the total transport needed. And we had talked about how in low latitudes there is direct thermally driven Hadley cell. The Hadley cell actually wasn't doing much of heat transport because the warm air was rising and cooling and then going and sinking in the subtropics, and air was moving from colder latitudes to warmer latitudes. So we had to add moist static energy to get net positive poleward transport. But the ocean did a lot of the work through the subtropical cells that we talked about, the ocean's Hadley cells, right? So ocean is forced from the top, so it's receiving net heat flux, and that has to be balanced by the meridional redistribution of the heat on some time scale. Let's assume some equilibrium, right? So if you talk about the surface heat balance, we had looked at dt equals minus 1 over rho ref Cw dq dz, heat capacity of the water, and the net heat flux. Just like momentum penetration, we had the heat flux penetration, and this obviously includes advection terms and the entrainment terms, etc. We had talked about the mixed layer physics, etc. We also had the salinity budget, which related to the net freshwater flux evaporation minus precipitation, which determines the salinity, right? So the heat content change of the ocean has to be related to the heat flux at the surface, either coming into the ocean or going out of the ocean, minus the divergence of the heat by the ocean. So there is heat flux coming in or going out, and then ocean is either bringing in heat to supply the heat loss or taking the heat gain and moving it out. So that's simple. So that's this equation. Ocean currents are moving the heat around. On some long time scales, the surface fluxes must balance the horizontal if we integrate from top to bottom, right? So heat content here, of course, is top to bottom, rho ref Cw, bottom to top, temperature times dz. Temperature has a profile, you just integrate top to bottom or bottom to top, and you get the total heat content. Net surface flux, of course, is short wave plus long wave plus sensible plus latent. We had talked about the sign convention. Typically, short wave is considered positive when down, but this book considers net flux out of the ocean as negative and or positive, and net flux into the ocean as negative. So heat transport by the ocean is bottom to top, u dt dz, where u is the vector. So there are zonal transports and there are meridional transports. We just integrate from the bottom to top. Okay. So, for example, warm water moving south and cold water moving warm water moving north in the northern hemisphere, cold water moving south would give you a net northward heat flux. Remember, ocean has a structure of transport, Ekman currents and thermocline currents versus abyssal currents, right? So we have to look at the net transport in that sense. So meridional heat transport, you can look at some meridional area in the atmosphere was the integral in the longitudinal direction and height. So we integrated around the Earth, and from surface to infinity, because the atmosphere has no boundary, of rho v times the energy times dA is the meridional surface, latitudinal surface area through which wind is going north, average, let's say, through all longitudes, right? So A cosine phi, 0 to 2 pi, 0 to infinity, rho v e, dz is the height, d lambda is the longitude, so A cosine phi d lambda is the integral along the longitudinal direction. We could write that as using our good old hydrostatic balance, convert dz to dp over g, and write it as a over g cosine phi 0 to 2 pi 0 to ps. So we flipped from 0 to infinity to 0 to ps by noting that the pressure basically goes to 0 at some height, and ps is the surface pressure. So we took out the negative sign of the hydrostatic balance by flipping this integral. That's all. Okay. On the ocean, in the ocean, on the other hand, it's rho ref Cw times A cosine phi, because longitude is lambda A cosine phi. Lambda is in radians, so you need the length. Lambda west to lambda east, because the ocean has boundaries. Each ocean is doing its own meridional transport. So unlike the atmosphere where you can integrate all longitudes, here you can only go from the western boundary to the eastern boundary, or the eastern boundary to the western boundary. And bottom to the top, V, meridional currents, dt dz, d lambda. Okay, so we are taking the depth here. And because there is no problem with the density in the ocean, we can take it out as rho ref and just do temperature and dz, and don't need to convert to a pressure coordinate, right? So the net upward heat flux, negative here, where the upwelling is actually soaking up the heat. Ocean is losing heat here, but this is positive here because they say heat loss should correspond to SST's convention. Doesn't matter. Okay, so this is the pattern that's giving the heat to the ocean, which the ocean is redistributing, right? So we will complete the story in the next podcast, but we are on our coordinate system with the local XYZ coordinates, and the rho ref Cw A cosine phi lambda west to lambda east, bottom to top, V dt dz can be written as divergence of the heat flux. Net heat flux has to be balanced by the heat flux divergence in the ocean. We say divergence, but it can be sign change to become convergence, but it's easier to just say divergence, which becomes minus a squared cosine phi at any given latitude. You integrate from phi 1 to phi, west to east, Q net, the net heat flux that goes between two latitudes, d lambda d phi. Okay? Meridional transport has to balance the net heat uptake. That's all it is saying in steady state. Okay? We'll continue this story in the next podcast, but make sure you understand the basic concepts, which are actually fairly straightforward. No heavy math. We're just writing simple equations and running through them a little bit fast maybe. In a classroom, I would go much slower, but in a podcast, I don't have any questions. I don't have any interactions, but you have the podcast, you have the book, you can listen to the podcast as many times as you want, as opposed to a lecture in the classroom, which you listen one time, right? So this should be easy to follow up again and again by reading and listening. I hope